Okay, so let's move on to part two. I want to talk about this today, but first I want to kind of continue about what we talked about yesterday on the first lecture. It was yesterday, part one, where we talked about the four fundamental operations of algebra, and I said that they were addition, subtraction, multiplication, and I'll use a dot for multiplication, and division. But really, and I want to stress on this, and somebody told me the theory about this is that there's only one operation in math, and that's addition. And you'll learn later in higher level calculus, you have a thing called series, which involves sums, and we use this big Greek letter sigma here. And you'll see that just about everything in math is modeled by addition. But we can easily see why these two, and I'll do these real quick, why these other operations that we should be already familiar with are all represented by addition. Subtraction, obviously, is if I say 3 minus 2, this could be written as 3 plus the opposite of 2. We'll learn that later when we start more focused on operations with negative numbers and things like that. There's an example that subtraction is addition. Well, multiplication is defined as repeated addition. So if I said 3 times 4, it's 3 added to itself 4 times. Oh, maybe. There we go. So 1, 2, 3, 4 would be 3 times 4. So multiplication can be represented by addition real easy, but a lot of people don't understand how division is represented as addition, and I'm going to walk over here to do that. And an example I'm going to do, let's use that, well, if we know that 3, I'll do 2 examples of these so you can see this. 3 times 4 is 12. I already put that in there. Well, the opposite of addition is subtraction, and the inverse of multiplication is division. So if I said that multiplication was repeated addition, that would indicate that division is repeated subtraction, and it is. So let's see this in action. 12 divided by 4. Okay, I'll do the opposite here so it's less work. 12 minus 4 is 8, and 8 minus 4 is 4, and 4 minus 4 is 0, and I subtracted 4 1, 2, 3 times, so 12 divided by 4 is 3, and that's how division is defined as repeated subtraction. And actually, when I teach division, I teach this method and when I do long division, because subtraction is not near as scary as division. Let's look at another example. How about 16 divided by 71? Some people can do the long division here, and see that 16 goes into 71 4 times with the remainder of 7. But not everybody can do that in their head. So if we subtract 16 here, using my repeated subtraction method, we subtract 16 and we get 11 minus 6 is 5, and 6 minus 1 is 5. We subtract 16 again, and we get 15 minus 6 is 9, and 4 minus 1 is 3. And subtract 16 again, and we get 23, and subtract 16 again, and we get 7. So we subtracted 16 1, 2, 3, 4 times, and what's left is 7. So that's a quick way to represent division in terms of addition. And some people actually, when I've taught this, they actually really appreciate this method because they do not, division is like one of the most hated things in mathematics. Okay, so now I want to talk more about this statement. Because I kind of introduced it yesterday with no background, and I really hate to bring something out, introduce something that I've never talked about before, but it was something simple as A and B are all numbers. But I want to focus more on what this R is. So this lecture is going to talk about real numbers and where they come from. And we're going to talk about some of the properties of real numbers. But to do so, we're going to have to talk about they're subsets, and I have to talk about what a subset is. A set is just a collection of objects. A set is a collection of objects. And of course in math, the objects are going to be numbers in most cases. In higher level set theory, sets can be functions. Sets can be other sets, which would be subsets. So if I say a subset is a part of a set. Okay, and there's different ways to define subsets. A lot of people will use capital letters. I'm going to say capital letter A is a set of numbers, and the set of numbers is 1, 2, 3, 4, and 6. Okay, and where this comes from, A and B are elements of R. Well, let's just talk about what are some elements of A here. We could say 2 and 3 are elements of A. Okay? And in terms of subsets, well, 2 and 3 form a subset. 2 and 3 form a subset, and the term for symbol for subset is this little, it's like a sideways horseshoe. This is a subset of A, and that's because every element in this set is also in A. So that's where the term subset comes from. So where do we need this? Well, the real numbers is a set of numbers. And the thing that it is comprised of a bunch of different subsets, and we use this fancy script letter R. I know I don't have it here, but both of these are usually generally defined to be real numbers. So let's talk about the most basic subsets of real numbers, and they start with the natural numbers. And these are the numbers that come natural to you. For example, if you had a big wad of coins in your hand and you dropped them on the ground, and you would start picking them up and counting them, right? Natural numbers are the numbers we count with. 1, 2, 3, 4, and so on. This ... is what is called an ellipsis. And it means that this pattern continues forever. And the natural numbers are usually denoted by a big script letter N. I'm not very good at writing the script letter N, but usually it's an N with 2 bars on it like this. That's better. So capital, or just a capital letter N, that's fine too. Okay, so the natural numbers are the numbers that we use to count with. And then they're also probably the first numbers that were originally invented back millions and millions of years ago when we first needed numbers. Because I'm sure got caveman fish, how many fish you catch? 1, 2, 3 fish, you know? That's probably where these came from. And then, actually, this next set actually wasn't the next set of numbers, but it's the next it's the next set of numbers that's built off the natural numbers, and that's the whole numbers. And the whole numbers is used capital letter W, and all it is the natural numbers. The only difference is the natural numbers and 0. The natural numbers and 0. So instead of starting at 1, the whole numbers start at 0. 0, 1, 2, 3, 4, ... And mathematically, if we could write this, natural numbers and 0, we could say that W are the natural numbers, and we use this horseshoe kind of looking deal. It's union 0 and the natural numbers. And another neat fact of these numbers are all built off of each other. We could say that the natural numbers are a subset of the whole numbers. And I'm already at 10 minutes. Okay, the natural numbers are a subset of the whole numbers. So, what's the next? The next set, and actually this set was actually invented before the whole numbers, before the concept of zero. The concept of zero was invented after the after the negative numbers, and integers are whole numbers and their opposites. Opposites being negative numbers. So these numbers start at negative infinity and -4, -3, -2, -1, 0, 1, 2, 3, 4. So they continue outgrowing this way infinitely, but they also, whatever the 4 and its opposite is there, 3 and its opposite, 2 and its opposite, and it's the whole numbers and the negatives, because we needed a concept of negative numbers. And these numbers are represented by the letter Z, because the German word for integer starts with Z. So notice that, so far we've got that the natural numbers are subsets of the whole numbers, which are the subsets of integers. Okay? So they're all built on each other. And in the next lecture, I'm going to continue and talk about the next set of numbers that we need to be more complete. Because this does not describe every number out there. There's another set after this, and I will use the next part 3 to get into that. And thanks for your time. Subscribe for when the future update goes online, and we'll see you in the next video.